Hello everyone. Welcome to the webinar on Midas. I hope I'm audible. Yeah. Okay. Good afternoon everyone. My name is Prathamesh Wane. I'm a structural engineer at Midas IT India. So today we are here for the webinar down to the basics of PSC box girder bridge. In this particular webinar, we will be going through the modeling, analysis, design of the PSC box girder bridge. So this will be a very basic webinar in which we will try to cover each and every point related to the modeling of the PSC box girder bridge, its different analysis such as the static analysis as well as the moving load analysis, and also we'll go through the design of the PSC box girder bridge. So this particular webinar will be conducted on Midas Civil NX. So, as we know that this particular webinar will be in two parts. First part, that is today, we will go through the introduction of Midas Civil Annex, and in the later part, we will go through the analysis and design of the PSC box cutter bridge. This will be the contents of our presentation. Firstly, in the part one, we'll see about Midas. Then we will have a small introduction to Midas Civil Annex. Then we'll have an overview of the structure. Then we'll do the geometric modeling today. In the second part, we will be covering the static analysis and the moving load analysis. Then we'll also interpret the analysis results and go through the PSC girder design in Midas Civil Annex. And finally, we will have certain question and answer session. So I request you to drop your queries or questions in the drop chat box. So I'll be happy to answer the question and answer the Q&A at the end of part one as well as end of part two. So about Midas, Midas has been established in the year 1989 and having a huge size of the company. The headquarters being in Southern Korea, and there are regional offices in US, UK, Russia, China, Korea, and India. We at Midas have a huge range of products ranging from Midas Civil and Midas FENX, which are quite advanced in the bridge analysis and design. Then in the buildings, we have Midas Gen and Midas Design Plus. In geotechnical analysis, we have GTS NX and SolidWorks. And in mechanical domain, we have Midas NFX and Midas FX Plus. So this is the Midas family in which we have plenty of softwares. Today, we will be going through the integrated solution system for bridges and civil structure. That is our flagship product, Midas Civil NX. Before going to that, these are certain signature bridges which are constructed in USA. So Wellington Bypass, then Leroy Selman Flyover, Port Access Bridges, Gallen Creek Bridge. These are all analyzed and designed using Midas Civil. There are also other signature bridges, including the cable stayed, extra dosed, as well as suspension bridges, which are used by using Midas Civil NX. This is the partial list of our top clients which are using Midas Civil, and this is the list of the DOTs which is concerned to Midas Civil NX. So this is the broad overview of Midas Civil and its capabilities. Let's go to the program itself and just see what is the workflow and how is the interface of the Midas NX. The viewers who are familiar with Midas Civil, that is the old Civil UI, is different, and the Midas Civil NX has an upgraded UI and upgraded facilities. So you could see that Midas Civil NX is having an quite a different uh, look as compared to the old Midas Civil. So let's go through what exactly the interface looks like and how it works. So here in the top, you could see that there is this ribbon menu and a lot of options in the ribbon menu. We'll just go through the options one by one. Then at the left, you could see that this is particularly the tree menu in which we can see the progress of our project uh, very easily during the modeling and the analysis phase. Then we have the modeling window in which the structural model is created. And then we have this part in which we can see the different view of the project. These are certain options which are the select, unselect, etc. which have been given here. And this is the message window, as you could see. We have the dynamic unit system in which we can change the units in between our modeling as well as the analysis stages. So we can change the units from here. So when it comes to the ribbon menu, you could see that there are certain key titles: project, view, structure, node element, properties, etc. So before going to them, I like to clear you that Midas Civil is a finite element software in which we are following a node and element based approach. So what is a node and element based approach? Is basically what we do is we create nodes and we join this particular nodes by using certain elements. The elements could be plate elements, plate elements, then plane strain, plate stress elements, or it could be solid elements as well. Today, in our session, we will be considering the frame elements, that is the beam elements only, but for modeling of this PSC box cutter bridge. So we'll go through this particular options one by one when we are in the later stage of modeling. So this was the broad overview of a Midas Civil NX interface. Let me just go back to my presentation view again. So as you could see, we are going to model the PSC box girder bridge today. But before going to the modeling part, we'll just see certain structural overview related parameters. So in this particular model, we are only going to consider restrict ourselves to the modeling of the superstructure. We are going to see in detail how the superstructure of this bridge will be modeled. So you could see this will be my superstructure in which we have the crash barriers, the bearing surface. Then as we go down, we have the bearings, the pedestals, the pier caps, and piles. So this is basically the structural model. But when we have to do an analysis, we cannot model the whole structure as a solid element indeed, right? So to make the analysis simpler, we have to make certain assumption in our analysis, right? So as you could see, the simplified version of this particular model is shown here, right? So herein you could see the bearing surface load is applied as an UDL over the entire structure. Then this is the crash barrier loading, as you could see at both the ends of this particular box girder. The bearings will be modeled as elastic links, and these are my supports. So in Midas, as you could see, the entire version can be represented in this aspect. So analytical model from the software analysis will look something like this. So in the 3D geometry, you could see this particular cross section of my box girder, and the whole box girder will be modeled as a single line element, which will be my beam or the frame element, which will be having 6 degrees of freedom on both the sides. As I am considering a modeling in which I will be considering the center top approach. So what is the center top approach? So as you know, when we model a particular section in any finite element software, the section can be represented in terms of a beam element, and the beam element will be passing through the CG of that particular section, right? So this will be something we call as the center modeling. So on the same cards, what is center top modeling is the structure or the section will be shifted in such a way that the modeling will now be done on the basis of the center and the top of that particular section. So what I meant is, for this particular section, we know that CG will be lying somewhere here, right? But now what I'm considering it to be the center top approach. So now my whole section will be modeled from this particular point, right? So this will be my center top point. Okay. So why this is done? This is done because we know that when it comes to bridges, the load is particularly applied on the top surface and not at the CG. So for considering simplicity in the analysis, to apply the bearing code at the top, then the crash barrier loading at the top, and also the moving loads at the top of this particular structure, I am considering the center top model in this case. So we know that these bearings will be modeled as the elastic links, okay? And this elastic links will be joined by the rigid links, as you can see here. And these will be my supports. Now, what are the elastic links and the rigid links? Basically, as you could see, rigid link basically establishes a load path without a need to model the dummy elements within the stiffness property. So now what I'm doing is I am rigidly joining the top of my section with the top of my bearing. Right? So this is basically joined by a rigid link. So there are two types of rigid link in Midas Civil NX. First is a rigid link, which is elastically rigid, and second one is called a master-slave type of a rigid link. So what is a master-slave type of a rigid link? Firstly, we have to define a master, and then we have to define the slaves. The master in this case will be top of my girder, and the slave in this case will be the top of my bearings. So wherever my master goes, the slaves will follow. So what this exactly means is, whatever will be the deformations in the master node, similar deformations can be seen in my slave nodes as well. So this analogy, wherever the master grows, the slave follows, is basically nothing but a master-slave type of a node. So this master-slave type of a link is given here. Nextly, we have the elastic link. So elastic link is mostly used to stimulate the elastic bearings in this case. So this particular elastic links can be given with different stiffnesses in the 6 degrees of freedom, 3 translational and 3 rotational. So depending upon the properties of my bearing that I'll be considering, the elastic link stiffness can be given. In this particular model of the PSC box cutter bridge, we will be using the pod PTFE type of a bearing. So we know that the pod PTFE type, wherever they are allowed or the movement is allowed, the stiffness in that particular direction is very low, and wherever the movement is restricted, the stiffness in that particular direction is very high. So we will use the same fundamentals to model the bearings of our structure. Lastly, we have support. Support basically denotes the restraining degrees of freedom or the restraining movement of a particular node. So basically, as we are not going to model the we are not going to model the substructure here, and that is the reason why we will not be considering the modeling of the entire substructure, and hence we'll be directly using the supports in this case as fixed type of a support. So this was certain introduction to the uh, structural overview that we'll be considering to model our entire structure. Now, when it comes to today's model, so as you could see here, that this will be my model that I'll be considering. So we will be modeling a 131.2 feet in length, a box girder bridge, which will be simply supported in nature, that is hinge at one end and roller at the other. So this will be the cross section of my particular bridge. This will be the position of my elastic links and the supports. The grade of concrete that we will be using will be C5000, and the tendon we will be modeling it with respect to A416250 normal. So in this way, the box girder will be modeled. Now let's move on to the demonstration part. So firstly, we'll try to define the material properties. Then we will try to define the section that we will be using in this particular bridge. Then we'll define the geometry of our bridge. Nextly, we'll define the boundary conditions, that is my supports and my bearings. Next, we will define the tendon properties in the bridge. And finally, we will define the tendon profile in this particular structure. So this will be the workflow of my today's modeling part. If the time permits, we will be also be assigning loads. If not, we will be assigning the loads and the moving load analysis in the later stage or in the part 2 of this particular webinar. Let's start with the material assignment. For assigning the materials or for defining the materials, we'll go to properties, then we'll go to material properties, and then we'll click on add. Let's define the concrete material first. So from the drop down, I will select concrete and I'll select the standard, right? So as you could see that in Midas Civil Annex, we have an inbuilt database of each code. So I'll be selecting ASTM 19RC and I'll be selecting the grade, that is my C5000 in this case. So you could see that the models of elasticity, Poisson's ratio, thermal coefficient, etc. is getting updated automatically. So this is everything is stored in the database. So I'll just click on apply. So you could see that my first material is defined. Next, I'll be defining the material for my tendon. So I'll be clicking on steel. I'll be choosing the code, let's say ASTM-S, and I'll be choosing the type of steel from the database. Let's say I have chosen A416250 and I'll just click on OK. So you could see that the two materials are now been defined. So I'll just click on close. Once we define the material, now we will try to define the section properties. So for that, I'll be clicking on section properties option and I'll click on add. So you could see that in Midas, we can define different type of sections, right from the PSC, tapered sections, composite section, steel section, and database sections. So this all type of sections are available in Midas Civil's database, and we can choose as per our requirement. So I'll go to the PSC type of a section now, and you could see that there is certain different type of PSC sections available. PSC 1 cell, 3 cell, N cell, etc. Currently, we will be selecting PSC 1 cell, as you have seen already in my presentation that our section is having a single cell. I'll name this particular section as, let's say, mid section. Then I'll try to enter the material properties. Then I'll try to enter my section properties. So you can see that there is a JIT diagram been popped up here. So depending upon the different dimensions which are being prescribed here, we can enter the values in this particular drop box. So before continuing that, I would just like to change my unit system first. So let me first switch to the unit system of inches and kips so that I could easily define my section. So this can be done anytime in between my modeling as well as analysis. I'll again go to section property, I'll click on add, and I'll go to PSC type of sections. Now I'll be entering my data. So my HO1, this dimension is basically 10 inches. My HO2 is 12 inches. My HO3 is 100 inches. So in this way, all the dimensions are prescribed in my presentation. I'll be entering them here one by one. Similarly, my BO1 will be 60, my BO2 will be 5 inches, and my BO3, which is this bottom dimension, it will be 105 inches. Similarly, the other dimensions I'll be entering one by one. So you could see that here in this particular image, our PSC section is getting ready. So I'll just enter the remaining dimensions. Yeah. So in this way, my section will be looking like as a part of the dimensions that I have entered. Herein, there are certain advanced options which are available for shear check as well as web thickness checks. So I'll consider the auto calculation of this particular properties. So these properties are basically used in the design of the PSC box girder. So the shear check and the web thickness are used to calculate the shear capacity of this particular section. So I'll put them on auto so that our program will automatically calculate this particular section. The change in offset command can be given from this particular option shown here. We can just change our offset from center center to center top as discussed earlier. I'll just click on display offset point and I'll just click on OK. So when I click on display offset point, you could see that here a red dot is lying, so which is basically my offset point. So in this way, I can define my section. Once I am done defining my section, I'll just click on OK and click on close. So in this way, we have defined our material and the section properties. So now it is time to define our geometrical properties of our section. For that, I would like to work in the units of kips and feet. So I'll just click on feet. from the menu. Then you can see here a node and element a tab is shown. So I'll just click on node and element. Then there are different options then available. Firstly, we'll create a single node at the origin. So I'll just click on create and then I'll click on create node option. So I'll enter my coordinates as 0, 0, 0 and I'll just click on apply. So you can see that a node is displayed here. So I can just select this particular node and now I'll be trying to extrude this particular node to create the geometry of my girder. So the extrude command is available here in directly. So you could just click on edit elements and here an extrude option is given. Herein the extrude type I've selected as node to line element. So this node will be extruded in terms of a line element. The element type will be beam. You can select other type of elements from these options as well. Then the material and the section I have already chosen. Now I would like to extrude this particular node by unequal distances and in my global X direction. So this is my global X, this is my global Y, and the global Z direction is basically my vertical direction. So I want to extrude my elements in a node in global X direction. So I'll just put X, then I'll enter certain dimensions 1.64, comma 39 at the rate 3.28, comma 1.64. So what this basically means is I'll be creating an element of 1.64 feet first, then I'll be creating 39 elements of 3.28 feet and last element will be of 1.64 feet. Then I'll select my node again and I'll just click on apply. I'll click on the isometric view and you could see my geometry of the girder is ready. I'll just click on close. So in this way, the geometry could be defined. Then now it is time to create the nodes for my bearings as well as my supports. So for creating the bearings and the supports, I'll go in the side view. I will be constructing my bearings below this particular node at this particular point on both the sides. So I need to translate this particular node at the bottom of my girder. So for that, I'll be using the translate option and I'll click on translate node. I would like to copy this particular node in Z direction and the distance I'll be changing to inches again for the ease, and the distance for which I'll be copying this particular node will be 122 inches, which is basically my depth of my girder. I select the nodes again which are to be copied. I select them and I'll just click on apply. I'm sorry for the inconvenience. I'll select them again and firstly they were copied above, but I want them below or the bottom part of my girder. So I'll enter the minus sign and I'll just click on apply as well. You could see the nodes are copied at the bottom of my girder. So I'll just go on to the front view. Now I have to translate this particular node to the left and the right? So I'll select this particular node again. I'll be changing my direction to Y. So this will be my basically my Y direction and I'll be translating them for 90 inches. So I'll just click on apply. You could see the node are copied now and now I'll be moving this particular node in the other direction for 90 inches. So minus 90 and I just click on apply. So this basically these nodes which are created are basically my representing the top of my bearing. I would like to create the bottom of my bearing as well. So let's assume that my bearing is having a depth of 12 inches. So I'll be selecting it to be Z. I want to copy this particular nodes in Z direction for 12 inches, so minus 12, and I'll just click on apply. You could see that my bearing top, bearing bottom, or the supports node are now created. Now I would like to assign the rigid links in between my girder as well as my top of the bearing nodes. So now what I'll be doing is I'll be assigning certain rigid links as we have discussed already earlier. So I'll be going to boundaries, and here you could see that in the boundaries there are certain different options available. Supports, so which are used to define different supports in the structural analysis. Then different springs are available, point springs, general springs, surface. Then we are having certain links, elastic links, rigid links, general links, etc. And there are different options available altogether, so which can be explored on the later stage. So for defining the links, I'll be clicking on this rigid link option as you could see here, and just click on rigid link. Then it asks us what is my master node. So as we discussed earlier, in this case, the master node will be the top of my girder and my slaves will be basically my top of the bearing nodes, right? So I'll just click on this particular blue box and select my node, which will be my node 2. Then I want this to be rigid, so I'll check on the rigid body option. So it is asking me to save. I'll just name it as example. I'll just save this particular file. Then I'll be clicking on rigid body so that my all degrees of freedom are constrained. Then I'll be selecting my slave nodes now. So these are basically my slave nodes, and I'll be clicking on apply. So you could see that my rigid link is now created with this whole circle which is shown here basically indicates my master nodes, and the nodes other than those are basically my slave nodes. Similarly, this thing is to be done from the other side. I'll quickly choose my master node again, and then I'll choose my slave nodes. I'll be clicking on apply, and the rigid link is created on the other side as well. So once you create the rigid link, now it is time to create the elastic links or the bearings. So for defining the bearings, the for this particular bridge, I'll be considering this as my hinged end and this as my roller support. So this is my simply supported structure. So this will be my fixed bearing. This will be having my transverse release. This will be my free bearing, and this will be my transverse restraint bearing. So let's go do this one by one. So I'll just select the fixed bearing first. So what I'll do is I'll just go to the elastic links. Then I want this particular bearing. You can see there are different options been available here. So what I'll do is I'll be considering the uh, only my rigid body actions, as you could see. So as my bearing is fixed, what I'll do is I'll restrain my X, Y, and the Z direction. So I'll just click on the SDX, SDY, and the SDZ options. So it means that the translation in that particular direction is restrained. Then I'll be selecting two nodes which will be indicating my bearing top and bearing bottom. So I'll just click on them. So you could see here that a link has been assigned, and the XYZ here basically indicates the local direction of that particular link. So similarly on the other side, I want a transverse release here. So for that particular purpose, I would like to release my Y direction, right? So I'll just uncheck SDY, and again I'll select the two nodes. So my second bearing is also assigned. Now I will be creating the bearing or the free bearing first. So, or I'll be creating the free bearing first. So the free bearing will be on this side of my particular girder. So for the free bearing, what I'll be having is I'll just uncheck my SDX here in this case, and I just select my two nodes again. So this indicates my free bearing, and in this particular bearing, this will be my longitudinally free bearing. So I'll just restrain my transverse direction in here. I just select my two nodes again. So in this way, we can ensure the simply supported behavior of my particular bridge. So once we have done with this, we are now okay to assign the supports to my structure. So I'll be again going into the uh, sectional view of this particular structure. So you know that the supports will be assigned at the bottom of this particular bearings. For that, I'll be going to the define support option. Then it will be a fixed type of support. So I'll be clicking on D all and R all. This basically means that all my translational as well as the rotational degrees of freedom are restrained. Now I'll be selecting my bottom elements, bottom nodes, and I'll just click on apply. So you could see that the supports are assigned at the bottom of my nodes. So in this way, the boundary condition could be assigned for a PSC box girder type of a bridge. Once we have assigned the boundary condition, now it is time to define the tendon properties in this particular bridge. So there are many methods to define tendon in Midas Civil Annex. So there are few options in which we can define the tendon by using the tendon template. Tendon template is basically a tool which is available in Midas Civil Annex, in which the tendons are considered to be in particular shape. So let's say a parabolic type of a tendon or a harp type of a tendon. So all these templates are readily available in Midas Civil, and user can easily consider those templates and define the tendon profile. The second option to do that is by defining the tendon profile in AutoCAD and then importing those tendon profile in Midas Civil. And the third and the final option is to basically define the tendon profiles with respect to the coordinates x, y, and z, or the space coordinates, and construct that particular tendon for the elements. So we will be sticking to the third option, which is the most basic option for now. So which is basically depend upon the uh, tendon coordinates which are in the global X, Y, and Z coordinate system. So for in that case, to define the tendon, I'll go to load. From this particular drop down, I can select pre-stress option. Then firstly, I'll be defining my tendon property. I'll click on add. So let's say my tendon property name is tendon itself. So you can select the type of the tendon. For now, it is internal post-tension type of tendon system. I can select the material which I have already defined A416. Then the total tendon area I will be considering here to be 19T15 type of tendons. So you can just click on this particular three dots and select the strand diameter from the drop down, or you can enter your own area as well. So I'll be selecting 15 to T or 15.2, that is zero point 0.6 inch of a tendon, and I'll be considering 19 number of strands in this particular tendon, and I'll be clicking on OK. So once I have defined this particular tendon, so you could see that I have to choose the duct diameter for now. So let's assume that the duct diameter is around 4.5, 4.3 inches, and my relaxation coefficient can be calculated with respect to the CAB FIP criteria. So you could see that you can choose the different classes and the yield and the ultimate strength, etc., the curvature friction factor, the wobble friction factor, and all the tendon related properties can be given in this particular dialog box. So once you define all these properties, I just click on OK and I'll close it. So in the tree menu, even you could see that all the things that we have done till now are shown here in this particular tree menu, right from the materials to section, boundaries, the elastic and the rigid links, as well as the tendon properties. Now I will be defining my tendon profiles. So to define my tendon profiles, I'll be going on to this particular option of tendon profile and click on tendon profile. I'll just click on add. Let's say my name of the tendon first up is A1L. So basically what we are going to do is we are going to define 8 tendons, 4 on the left side and 4 on the right side of this particular bridge. So I'm already having certain tendon coordinates. So we'll be using those tendon profile coordinates in this particular bridge, or else you can also use the tendon template profile option, which is available in Midas Civil NX. I'll choose my tendon property to be tendon. I have to assign this particular tendon to my entire elements, right? So I'll be clicking on this select all option which is available here. So all my 41 elements are now selected. The input will be 3D type and the curve will be round type. So we are also having an option to consider the transfer length. The transfer length could be user defined or it can be auto calculated as well. For simplicity, I am considering it to be auto calculated for now. Now it asks me about the uh, coordinates. So I'll be just changing the units to mm for now because I have my coordinates in mm. So I'll go to my Excel sheet. So here you could see that I have an Excel sheet in which I have mentioned certain coordinates. So for A1L type of tendon, so I'll just select this coordinates. So you could see that my X is ranging from 0 to 40,000. So which is basically my entire length of the girder in mm. I'll just copy this and I'll just paste it here. So you could see here in the diagram as well, the tendon profile will be looking like this. Then Then I am asked to the point of insertion in this case. So the end I will be considered for insertion and the element for which the insertion will be taking up will be the first element. So I'll just select the first element from the uh, modeling window. Then I will be giving an x-axis rotation angle. So what it basically does is it rotates my tendon profile by certain degree to get accommodated in my slant edges. So you could see that this particular edges are slant to certain degree and I want my entire tendon profile to be slanted in that particular fashion. So I'm considered a 5 degree of rotation. So -5 I have put, and I'll just click on apply. So you could see that my first tendon is now visible. So if I go in the elevation view, so you could see that my first tendon could be looking like this. Similarly, now I will be assigning a tendon A1R, so which will be on the other side. So all the other inputs will remain same. I'll just select the entire table and click on the delete button to delete my tendon coordinates. Then again, I'll be going to my Excel sheet and I'll just copy my tendons. The tendon coordinates are again pasted in here, and the point of insertion for this particular tendon profile will be my first element only, and the rotation will be now +5 degrees, right? So I'll just click on apply. You could see that the other side tendon is now also visible, right? So in this way, we can define the tendon profiles A1L and A1R. So in the similar way, I'll be defining the other tendon profiles now. So let me just go back to my Excel sheet and define the remaining tendon profile for you. I'll just click on copy, delete this data, click on paste. So my name will be A2L now. This will be -5. Click on apply. A2L is defined. Now I define A2R again. As Midas Civil NX is quite compatible with Excel related functionalities, so you can easily enter all the data which is there in the Excel sheets directly in Midas Civil. So in the same way, I'll enter my A3L type of attendant now. So you could see that one by one, all the tendons are showcased in here. My all the tendon data is now being used. Okay. So in this way, my all 8 tendons are now defined, and you can see that all the 8 tendon data is now visible in this particular tree diagram as well. So if I go to the elevation now, so you could see that my 4 tendons on one side and 4 tendons on the other side are now visible. So in this way, the geometry of our structure can be created in Midas Civil NX. So now I have created the total geometry of this particular structure. Now I'll be interested in creating the static loads. So before ending this particular session, I'll be just show you how the static loads are created in Midas Civil. So for that, we are having this option of load. Then we are having different load been given here. Static loads, temperature, pre-stress, moving load, dynamic loads, etc. So we can define the static loads here. So different static loads such as the sulfate, then the SIDL, the crash barrier load, and the moving load is will also be entered. So for the moving load, we have an ASTO LRFD standards been available here. So in that, all the vehicles related to ASTO LRFD are shown in here, like the HL93 truck, HL93 tandem, HS20 fatigue vehicle, etc. Loadings for the moving loads will also be considered in the further lectures. So in the part 2, we will be considering the design as well as the analysis of this particular structure, and prior to that, we will be learning how the different loadings are given in Midas Civil NX. So let me just jump on to my PPT again. So herein the part 1 is concluded. So let me just jump on to the if we have any questions in the chat box. So apparently we are not having any questions in the chat box for now. So yes, this was it from the part 1 of the webinar series. If you have any question, any queries, you can contact us on the global support portal, and we will be happy to answer all your questions and queries there. So let's meet for the second part on the 28th of March. So thank you. Have a great day.
Thank you for joining, everybody. Again, the next session will be March 28th. We will be sending over the email with the recording and also with the materials. You will be contacted by a Midas representative to share those information. Thank you again and have a great day.